Dimension.
Не, размерность.
Dimension of motion. In other words, where do we move? We move. This is one dimension. So there's somewhere here 0, and there is plus infinity here, minus infinity. So something is happening.
So one small comment in Russian. Видите, дело x, t принадлежит прямой, то есть размерность равна 1.
Ну да, это понятно.
So everybody understands.
Just to give another idea.
Yes, well, that's for later. For later, we can see. Okay, now, for example, and now why it is so easy? Because suppose there is some point here x, which I will call x with a little bar over it, at which, at this x, f at x, this bar, is 0. So, some say f of x is x squared minus 1. So at x equal to 1, x equal to minus 1, this is 0. But this means that then this is 0. Which means at x bar is called, let's find, remember now the Russian word, how is it? The fixed point?
Точка равновесия.
Точка, point is точка.
Равновесие.
Не равновесие, а...
Точка равновесия.
Точка равновесия. Точка равновесия, fixed. Now, fixed, okay. Now, so what happens now? Equilibrium point. Now, somebody will say, okay, suppose I am here. Use another color. Something, this is yours? Yeah? No. Okay, so blue, I need some red, something like this, some green, red, etc. Okay, so suppose you're here. Now, I ask you here, at this point x. Now we are moving. What is your name?
Misha.
Misha. Now, Misha, you tell me, I put you here now. So if I put you here, at this point, you say, this is 0, this is fixed point. Now if I put you here, where do you go?
Left.
This is left, okay, that is one idea. But why left?
Because we...
Why left? Why not right?
Because we moved to fixed point.
Very good. Yeah, so, well, yeah, we moved to fixed point. But now left. My question is, will I go this way? Or will I go, you said we moved to fixed point. What's your name?
Denis.
Dennis. Dennis, very good, Dennis. Okay, no, you say we moved to fixed point. Why?
Because maybe all systems dynamic...
Very good, very good. Now you're talking. Yes. Because you think, No, that's not true. Because suppose I give you a ball, I put it up on top of this place, and it's a fixed point, and I ask you to tell me what happens if I put myself in this точка, in this point. What will it do? It goes away. And on the other side also, it might go away. So there you see, you say, well, what happens if I have a little system like this? Equilibrium. If I am here, I will definitely. So here, I will do this. But how do you know which one is happening here? Does anybody have an idea? In mathematics, we always must have ideas. Mathematics is not only formula, derivative, integrals, it's also thinking. Thinking. What is important? Right here. Now, you all remember that this point x, let's write this point x as x bar, is very close, plus another function xi of time. Xi is a Greek word, difficult to write, xi. In Russian you don't have a letter like that. But it's very useful in mathematics. In the books you see epsilon, xi, eta, theta, all the Greek letters. So we write xi whenever it's small. So we say xi of t, I want to consider only xi of t very small. Very small. But if that is the case, then I can go to this equation and I can write dx dt. Now I can put this terms into this equation. And all of a sudden I have dx dt on x bar is 0. Then I have on the left dx dt. On the left. And on the right I have f of x bar plus xi. Now, can anybody remember what do we do if we have a function evaluated at x bar and xi is small? What do we use? Some type of series, expansion.
I don't know how to say.
You heard Taylor?
You can
Have you
say
heard?
in Russian.
Yeah, say it in
Yeah,
Russian.
translate.
Ну, мы, по сути, просто превращение делаем небольшое, да? Вот.
Well, it has a name. Mr. Taylor. Mr. Taylor.
Taylor. Formula Taylor. используем.
Formula Taylor, you know.
Taylor formula.
Taylor formula. Huh? Taylor formula. Taylor formula says that f of x will be equal to, okay, Taylor formula, f of x is equal to f of x bar plus xi, and this is what we call Taylor's series.
Ряд.
Yeah, right. Taylor series. Okay, so what is the Taylor series? That first is f of x, yes, then it is plus the derivative of f, right, evaluated at this point, x, then it is xi here, xi minus x, but x bar is 0, xi is correct, that's xi, plus second derivative, f double prime, we know derivative, so our function f must be differentiable. Different derivatives, 1, 2, 3. Right? Differentiable, bravo. So it must be differentiated 1, 2, 3 times. We can stop here. Because then we go to terms that are very malenky. These are small now. Because we said xi is 1. So if you are going to go close, xi squared is very, very small. And it's no need to, because xi already is there and will help you. So now you see what happens. This is 0. So Mr. f of x is replaced in the equation there as what? There we go, right here. What do we write now? F of x bar, but that is 0. So the first term is f prime of x at the point x bar times xi. Plus, as we write terms of order, xi squared and a higher order terms. So now, I can decide for you if it's this picture or this picture. Because dxi dt says, if you go xi a little bit away from this equilibrium, or here, xi, here plus x plus xi, go here, then the movement will be decided by the derivative of the function at that point, times xi. That's a constant. Now, you see that if f prime of xi is positive, what do you think xi will do in time?
Move right.
Huh? Move right, yes,
Right.
because xi will grow. Huh? Dxi dt,
Yeah.
right? If f, the derivative is, let's call this number here r, something like this, then dxi dt, you all know, equals r, it's a constant, times xi. Now I ask you, we solve this equation, but the solution is very easy. Xi of t is equal to some constant c, to start with, e to the r t, right? Oh, it's very simple. The simplest, even in high school. Children, they know this. We are in university, we should know. So the answer is everything depends on the sign of the derivative, r. Look here. As you move away, what is the sign of the derivative of f prime? Right here is, yes, so we have the first things will go. So if r is positive, then if the derivative is positive, then we have, we will move away from the fixed point. So this will be decided here if x is equal to some constant times e to the rt, and r is positive. If r is negative, yes, this is negative, as it happens here, derivative is negative, then you will go down to this point. So then the solution, if you go this way to the point, will be x equals c e to the rt, but rt now is negative. Let's say minus t. So the x will tend to go back to the fixed point. So we don't know. We must check and solve a linear problem. You see, this is called a linear problem. And in Russian, linear? Linear problem. Linear problem. Now, we may start with a difficult problem, non-linear. We don't know how to solve it. But I show you that if we go to the point, then we can understand what happens near it. Okay. So that is a good introduction to what is called local dynamics. Very close to a fixed point. But that's very easy. Now, that's why one motion in one dimension, this is all, finished. Dynamics in one dimension, this is it. One line. What can you find in one line? Fixed points. Now, you see, what is a little strange is that the derivative could be positive on this side, negative on that side. So maybe from one side you approach it, and from the other side you go away from it. That's also possible. Okay? Like this, for example. If you're here, and this is a fixed point, well, you go down here, whoop, to this fixed point. If you go to the right, the derivative starts to be negative, and then the mass will go away. This is a little circle, rolling down again. So this is also possible. Now we know this point is half stable. Stable, but half. Huh?
Полустабильная.
Right. Okay, end of the story. One dimension is very, very easy. And now you think of two dimensions. Now, in two dimensions, I can have, for example, let's say, have you heard a little bit of a physical problem? It's called the harmonic oscillator. Let's see if have you heard?
Маятник.
Bravo, you remember it. Very good. So, harmonic oscillator here, it has also a mass point. So, and the spring is not stretched, it's there. You can either push it or push it that way, but now it's there. Now, I pull it away or push it in. What equation do I have to solve? Now we know from the times of Newton, the great scientist, Isaac Newton. And at the time, Isaac Newton also in the academy, scientific academy in London, he had other friends and they all understood how to solve. Only Isaac Newton thought of the space, of the universal law of gravity. That was Newton. But a lot of his scientists there, they knew how things are moving, what's happening. And So there was one such person who said that I will tell you what is the differential equation. There is a mass, and there is now what is called, I would have to think of the Russian words, right? Acceleration.
Ускорение.
Ускорение.
Now, you know, very good. You guys are expert in English. I can see you know. Now, acceleration means that mass times acceleration must be equal to the force. Now, what is the force?
You give
Сила. Power.
dt squared.
Dt squared, I'm sorry. So,
dt
dt squared, right? So now we have second derivative. That's all. I will not go to 3 or 4. But already here we have something interesting. What is the Hooke? One of these scientists was Robert Hooke. And he told,
Гук. Закон
Hooke, because H becomes
Закон
gamma in Russian, right. No, very good. So Hooke said, I know the answer must come from experiments, and the answer is minus some constant of the spring times x. Okay, everyone? Have you seen this before?
Yes, in school.
Yes.
You remember that, okay? Very good. So now, we know how to solve it. Everybody knows how to solve it. And now, the answer is that we have one integral, let's say, so if we solve this, we find that we have a total energy of the system. We can integrate the equation of motion. We have 1/2 mass times the velocity derivative dt all squared, okay, plus 1/2 k times x squared. And all this is equal to a constant. So it's all solved. And if I call this problem here, but I don't want to solve things analytically. That's not my problem. I want to solve geometrically. I want to show you geometric dynamics here. How to do geometry. Now here, for example, now we have what? E equals to, let's write it again, 1/2 m. This I will call the velocity squared. Yeah? And this I will call 1/2 kx squared. Okay. So now we see that instead of only x, we also have now a second variable, v. And there is no way we can do it now in one dimension. We have to go to 2 dimensions. And in these 2 dimensions, I have x here and v here, which is the velocity. Yes. And now, you know 0 is 0. Means that nobody touches it, it's not moving, 0 is 0. Somebody now moves it a little bit, and what it's doing? Movement around this point. So there we expect nearby here to have a motion now in 2 dimensions, no longer in 1 dimension. And now, as you see, now what kind of curves are these? How do we call them?
Circles?
Be careful. Are they circles?
No.
Not always, right? How do we call them in Russian?
Ellipse.
Ellipse. So you could say ellipse also. Why? Because as you see here in this equation, energy, you see, energy is free to choose here. Let's concentrate on this. So what are the variables? V and x. Right. It looks like a circle, but then these two are not the same. So they are ellipses. Very good. So generally, it's an ellipse. Now, do you need to know the exact solution? If I have this picture, geometry tells me the whole story. You tell me, how much energy do you put in your oscillator? What is capital E? You say, capital E, I give energy 1 unit. Okay, I go here, and I put E equal to 1, and I find this curve here. E equals 1. Then another guy says, I choose to put E equal 2. Okay? So this is called a one-parameter family. It's a family of ellipses depending on one parameter energy. And the problem is solved. There is nothing to do anymore because you are in two dimensions. If we continue later on, and you are good students and you come around back, then later on I can tell you more things about two dimensions. And because the problems can be difficult, let me tell you okay, let's say for example, okay, so we solve this. Does this mean we can solve all problems in two dimensions? Of course not. The very nice thing about this equation that you all know from high school, this equation is that it is called linear in X. In X and also in V. Right? Sorry, no, it doesn't feature here. Just the equation, we have a derivatives and we have this. Now, you say to me, but this is second derivative. Why? Why can I not go to the plane and see two functions? I want to have x1 and x2. So why have second derivative? It's not very nice. I would like to see dynamics only first derivatives. Why? Because it's better. I can solve first order easy, more easy. So what I'd like to do, you say, is that, okay, very good, but can you make it more theory about it, more theoretical? Well, you say, okay, so let's write the following equation down. Let me say that dx dt, I call it a variable v. I call it v. And so you see here, I already called it v over there. Now, and then I have a first order equation. So in two dimensions, I have two equations. If I had three dimensions, three equations. But they are all first order. So what was this? This was minus kappa k times x, that derivative, correct? And, oh, nothing else. That's so easy. So you say, this is a linear problem. Yes, I don't see x squared, I don't see v squared. This is linear. So that's very easy to solve. In high school, of course. And now I will ask you, did you do something else in high school? Let me...
You forgot the mass, I think.
Yes. Yeah, what is the
mass M.
Pardon me? Did I miss something?
The term M.
Yes, you're right. You're right. M. Yes. Because, yes, you're right. Because this is M times, no, this is the second.
This is fine. And
this is fine.
In the second equation, there should be M.
Yes, you're right, absolutely. Thank you very, very much. Very much.
Divided by M.
Yes, by M. Very good. Now, you may remember even from high school that this we called omega squared because it is a kind of frequency in Russian.
Частота. Частота колебаний.
Часто is quickly.
Frequency of oscillations means in Russian частота колебаний.
Okay. This is frequency. So you say, that's important. Now I know period, time, frequency. That's a very important constant. But the problem is linear. It's very easy to solve. And there's the answer. Energies. A family of energies. Everything on the plane. And then I tell you, okay, but I come to you and say, let's look back at this problem from physics. Mass times acceleration. Okay, as before. Here I have also
dt squared.
Sorry, yes, I forget it. Minus kx I have here, right? And that's it. Now we know where we started. But now I am going to drive this with another omega. So, did you remember, have you seen this in high school?
Yes, it's
Mhm.
base.
Huh? With?
Base formal for
That's right.
mechanic.
Mechanic. Okay, so we know how to solve this. It's a linear system, we all know. But can you do this in 2 dimensions? No.
Repeat, please.
Huh?
Repeat, please.
Repeat.
В двумерном случае что делать?
Can we say
Ah,
that the motion here is in 2 dimensions?
Двумерный.
Нет.
Если двумерный вектор.
у тебя что делать с двумя вверх?
Not anymore.
Что делать в случае двумерного вектора? Да?
Not anymore. See, what you're doing is, so that's why it's good to think also about physics. I am pushing this, it's moving, but now I'm also pushing it with my own hand, with a force. So now, it's not going to stay on these ellipses anymore. Because as it's going like this, you push it. So what is it doing? It starts to move like this. Now the motion will be, how will the motion be now? Here. Make it dry after a while. So shall I use? So we have here X and V. And now, since it's not turning around, the motion will start to go like this. As you push it this way, it goes out. Then it starts to go in. Then it starts to go out. So, what is this mess? Mess is confusion. Is now this point cannot be a unique solution. Right? We know that. So, this is called a projection. Something is happening in 3 dimensions. And so, to understand it, we must plot here, let's plot here, now, a new axis called time.
Oh,
Huh?
okay. That's good. So we can say that in 1 dimension we got, as an idea, in 1 dimension we
Very
got
good.
only one moment. But in the second, already in 2 dimensions we got not only one, and because of this, in time we don't got constant movement for this, and we need to add the new.
Very right, exactly.
Yeah.
Because now, your name was this?
Arseny.
Arseny, of course. I remember that. Arseny says, of course, because it says that if you start here somewhere, this is time t equal to 0, right? And this is my beautiful x and my velocity. Now you go like this. And if you want to go out, where is it here? Okay, go out. Out. And then you can come back here again. And then you can go out again. No problem. This is an orbit in 3 dimensions. No problem of uniqueness. You know now, you see it, and you know where it will be. So the dimensionality increased. And now, I have a question. How do I understand this? It's going, is it doing something crazy? Up and down, and then up and down. What is it?
No.
It's not chaos, huh? No.
Position to
Superposition of
superposition.
2. Very good. Of 2 frequencies. An omega small and an omega great. Aha. So now, it seems to be important for me to look at times to stop this. So put this here, right here, let's put another such coordinate system where at t equal to 2 pi over omega. As you remember, frequency, and this is like the period of this motion. So I look here, where am I? Right? And then I go further down here to look at another pi equal, this is T1 if you like, this is T2, is what? 4 pi over omega. Why? Because this equation here, where are we? Did I write this down? Here, for example, yeah. This equation here, every time t equals 2 pi over omega, 4 pi over omega, this returns back to the same point. So it's the period of this function. So that's an additional periodicity. Question. X here has its own periodicity, a frequency, which is little omega. So now I ask you the question. The relationship between big omega and small omega is important. Why is it important? Why? Is this going to be like a clock? A clock, that tells the time? What is the clock? Yes. Will it be that every hour it comes back to the same point? 2 hours to the same point? Is it periodic? If this was the motion of two planets, the Earth and the Moon, and one is going around the Moon, so the Moon is going around every 1 day, and the Earth is going around the Sun every 1 year. Question, will they come back to the same point exactly?
No.
No. But, okay, now come down from this space, down to this problem. Why not? Maybe they do. I'm not, you cannot say no, definitely.
Yeah, right.
Maybe they do. What is the question to ask?
Can
When will they come back to the same point?
So we wanted to say, we wanted to predict, will they come back and wait?
Yes, will it be periodic? In other words, here, imagine this problem is like a simple problem in a factory in business. We go like this, and and I want to know, is this going to go periodic? If not periodic, it's possible. You remember the solution in high school? This is going to go to bigger and bigger because of a resonance. If omega is equal to capital omega, we have this thing is going to boom, break. Because omega little, small, is a number of times capital omega. In other words, the two are in resonance. What does this mean mathematically? Resonance, here that is to be avoided. Resonance means that omega over capital omega is equal to a rational number, n1 over n2. This is called a resonance. Let's say this, for example, can be whatever. Example, 3 over 11. This means that after some time, a long time, one of the oscillator will have completed, let's say, 3 times oscillation, 3, and the omega capital of the driving, 11. And one goes 1, I keep pushing you hard, so you go 1, and you go back, I keep pushing you. You go 3 times, and we come back to the same point. That is resonance. And same thing like with a clock. 1 hour, both of them move around, both the clock, the hands of the clock, they go around. One has a period 1 hour, and the other has a period 24. So the resonance is 1 over 24. So this is important. Now, by the way, when will the boom break up? Not always. When these are exactly equal. Here they're not. So if you solve the problem and your analysis go back to high school and you solve it, you will see that in the solution, x of t, there is now a part of the solution that we knew before, plus, if I recall well now, a over n square, now omega square, minus capital omega square, times sine omega t. And maybe I need, for my solution, to put even a cosine, if I need to. Cos omega t or something. But the important thing is, sorry. This is, yes, capital omega. And this is the cosine, let's say omega t also, but the same denominator. So only when omega, if this holds, and this is 1 and this is 3, then no problem, denominator. It simply means that this will grow and then come back again. Grow and then come back. They will go to infinity only if omega is exactly equal to capital omega. So you see, you hear things in high school, but then you learn it by heart. You don't hear the reason behind it. How to go, that's all. Well, the same thing with me. In high school, I learned everything, and then somebody asked me a question, I didn't understand very well. So it's important in mathematics to understand a problem from every side. Okay? Newton was a mathematician, many mathematicians, but they also look at the physical aspect of it. Okay, so here is a practical problem. What happened? All we did was just add this stupid little sine omega t. This is it. I mean, as we say, this we learned how to do it in high school. So what's the big deal? We did not imagine that to really follow the motion, we needed to introduce the question of time. And now comes my important conclusion, which will bring me to another subject, because this was an introduction. What is the conclusion? It is difficult to follow something in 3 dimensions. So what am I going to do? I'm going to choose 2 dimensions. And I will solve the problem, I will try to understand the problem in the following way. As we see here, the dynamics is repeated between this point and this point. So, why don't I say to myself, well, this is the problem. I have here x of t, but this is a. And I have, let's say, the velocity. I said, okay, the velocity, v of t, but it will be at tk. And the points I will put here is k equals to, what do you think? Sorry, tk. K is equal to tk. I mean at tk is equal to k times the period, capital omega. That's my problem. This guy, every capital omega stops and gives me a push, 5 omega. And then I have to follow. So now, everything you see here, unraveling in 3 dimensions, I now have it as a sequence of points. Because what does this mean? It means that this point goes to this point, and this is a tk, and this point is a tk plus 1. 1 period later, and later it's here, and later it's here, and later it's here. Now this is never going to cross, because this is unique solution on this plane. It is the same dynamics. Just put it on, for convenience, on one plot. So don't worry about non-uniqueness. Everything is fine. So what happens? You may see this here, and then it may go there. Now, on the same, by the way, it's not continuous, right? So it's following points going here. Now, will it go to infinity? Well, if you see them going away, hey, guys, wait, watch. Maybe we hit the point. Here we have resonance. But no, after a while, it comes back. Okay. And now I say, suppose omega and omega are rationally dependent. If omega over capital omega is a rational, then when one of them has closed, as we said, with 11, 3 times, one has closed n times, and 1 times, the other one has taken n 2 times. Question, are they back to the same point? Is this is, in other words, a periodic solution? The answer is yes, because that's why this was the case. If capital omega and omega have this ratio, then the solution will come back after I don't know how many. You see, for the clock, hands on the clock, one of them goes around like this, the other one goes around slowly. You have to wait. In 12 hours, there's a period. In another 12 hours, another period. That's exactly what is happening here. So, okay, then a good student asks, right, if it is not irrational. After all, you know, rationals are very sparse, rare. How do we say?
Разрежение.
Very few, uncountable. Irrationals are, rationals are countable. Yes, it's right. And the other, so it is very possible that one is not 3 times the other, or the Earth and the Moon. They're not 100,001 and the other one is 500 and 2001. No. So the more common thing is that is irrational. Irrational. So there is no periodic solution. This will continue along this green curve. It will not go to infinity. No. It goes to infinity only in this very simple case, where omega is exactly equal to omega. But here we have omega over omega equals to square root of 2. Pi, 3.14. Some irrational. There is never going to be a periodic orbit. The idea with the planes is a very good one. Sure. It's every 2 pi over omega, 4 pi over omega, 6, yes, 6, 3 times, 6 pi, 8 pi over omega, everything. That's fine. But what will we do is another thing. So most probably it will not be periodic. And then comes the question to the student. What does it mean, not periodic? It means it will continue to go and never come back to the same point. Well, that's not so bad, but okay, that's interesting. Have you traveled in a bus?
Yeah.
Yes,
Every morning.
Every morning, yes. But this bus, not bus that comes to the university, the bus from the school that took you on a trip, an excursion out in the country. And then you sit on the bus and the 2 wipers start to for the rain. Their day was raining and the 2 wipers are moving like this. Well, the mechanism tells them have exactly the same frequency. It's the same thing. So the 2 wipers begin like this. Have you observed what happens during the trip if you follow this phenomenon? What do you think? What do you remember happens? Do they always go like this? Exactly. See, they're not connected. So one doesn't exactly pull the other. They're simply there. They start at the same time. So it goes like this.
No, we want to say that
If you wait, right.
Yeah. It's no resonance because if be resonance some day, okay, it can.
Oh, the others. I've been in a bus. I watched the bus. Yeah, they go like this. Right. You're right. And then they start to go opposite way, out of phase. It's called. And then they start to come together again. So what has happened? Like here, they have gone. They've oscillations have gone out of phase and then back in phase and out of phase. So that's not synchronized exactly. It is moves also. It doesn't repeat exactly the same thing.
Do they do that?
What?
They always go together.
Yeah, no. They don't always go together. The ones because they're independent. So as they go like this, they start to go differently. And then they come back, you see, they're far away. Now, I'll tell you now just another story, just to remember. The great Dutch physicist, Huygens, put on this is a wall here, here's a wall, and he put 2 clocks on the wall. It's a great Dutch physicist, Mr. Huygens, very well known from wave theory, 1700. And there's here a clock, and the clock has pendulum. And the pendulum goes like this, back and forth. And there's another clock here. And the pendulum moves like this. Now, Mr. Huygens observed that after a while, the two clocks synchronized by themselves. So that you, just Google it, huh? You will find it. Synchronization. And synchronization, just look at it up. And I give you this, the name is a very famous Dutch physicist. If I remember well, it's U.Y. Huygens, the Dutch physicist. So they synchronized. But why they synchronized? Because they were in communication with the wall. Amazingly enough, this little coupling between the two clocks leads them after a while. This you can do on your walls of your house. You can take two clocks and you will see, but I think they have to be more or less the same type of clock, not a small and a big one. It's easier to wait. And then you will see two same clocks, they go like this. This does not happen in the bus because one is here, the other is there. There's not enough communication between them. If there was, then they would synchronize. Now you see all of a sudden all this discussion from 2 dimensions, nothing to it. Imagine if we go to 3 dimensions. So now we don't understand much about the motion. We have to start from very simple models. And especially, now you may think, as many mathematicians, Poincaré was the first one, a French physicist, polymath mathematician of 1890, let's say, 1090, Henri Poincaré. He said that, well, let's see. Let's suppose I plot a point here, here. And that happened here for tk, where I was here. And then at tk plus 1, let's go back to this plot. This plot was very nice. It showed us something. Now, then after here went here. Then from here, I went here. tk plus 2. And so on. Question. What is the force? What is the operator, let's call it F, that takes me from here to here? It's an operator, it's a function F, that takes a point to another point. So I have discretized the problem. From a continuous motion, I have to solve, and you know, these are linear oscillators. Of course, the solutions are so easy. Sinusoidal, cosine, function. Imagine if I made it non-linear, you would not be able to solve it. But what do you want to know? The behavior of the points. Are they periodic? Are they quasi-periodic? Do they go to infinity? Why should I solve the differential equations, which are difficult to solve, if I know this F from here to here? And so now I call a point on this graph. Let's call it, here will be a 2-dimensional point. So how should I write it? Let's call it, this is a point tk. I have a point P of k. And then I go to the next point, and I have pk plus 1. So I need the function f that takes me from pk to pk plus 1. So now I can write p of k plus 1 equal to some function of p of k. And I have brought my problem into the case of discrete dynamics. All this was to introduce the subject today. If I started today by telling you discrete dynamics, we study this. You say why? What's wrong with continuous dynamics? But now you know it's difficult to study something, continuous dynamics. If you look at the sun, the moon, and the earth, do you care where they are all the time? No, I want to know if I come back in the summer, will it be the same summer? Hot, cold, everything. I want to know every time the Earth comes back, what is going to happen next year in the summer. I don't want to know all the year, just the summer. But that means I have to look at the problem in a discrete way. One time, two times, and that is the case of discrete dynamics. Okay. Very good. So it's an interesting, beautiful game now. You will hear. I'm sure you haven't heard it in high school. And that I want to start to tell you this. How much time do we have? Another half hour, maybe?
Yes, sir.
4:30. Okay. We started, and then we can continue next time. So let me begin something very simple. This was, of course, in 2 dimensions, right? So we need to go pk to t, from this point pk to pk plus 1, 2 dimensions. So well, that's a little difficult. Let me try to do it in 1 dimension. So here we go, erase everything, but now you see why the continuous dynamics is not easy to solve. Mathematically, it's very well defined, everything is fine. You can do this problems, you can solve it on the computer, absolutely no problem. But do you understand what is happening? And the way to understand it is to go now to something I call discrete dynamics. You see a lot of fun, there's a lot of nice things happening now, and I hope you will enjoy that. Now, so this is called discrete dynamics. And discrete dynamics, I will begin from the simplest one I can think of. And that is, first of all, I'm not going to care about x of t. Now, time is discretized in 1 step, 2 steps, 3 steps. So I want to know how to get a point, and now xn all are in 1 dimension, r. So we place ourselves again here. Now you say, you remember, oh, 1 dimension, we know everything about 1 dimension. No, you don't. You know it when it is continuously on 1 dimension. If I tell you now, I'm going to jump from this point to this point, and then back this point and this point, you know nothing. So all of a sudden, it's a new game. It's a new game, and in order to study it, I need to study this problem. And that's the problem number 1. This will lead us to a wonderful world of fractals and chaos and many, many things. But I want you to understand the first basic ideas. How are we going to do this, to study this? Well, let's take a linear system. Where do you start? Always, when you get in a new subject, you want to know what's happening in linear problems. A linear oscillator gave us a lot of interesting things. So what is a linear problem? A linear problem is xn plus 1 is equal to some real number, r, times xn. Okay, now if this was a differential equation, there was no problem. I would know this is if r times x, then I solve it and I have x equals some constant e to the rt. Fine, so since this x is a fixed point now, this is continuous, x is 0, this is 0, so this means that solutions will go away. If r is positive, they go away. If r is negative, they go to the point. So that's what linear analysis tells us. Let's come over here. Is it the same idea? Well, let me see. This is a lot easier. It seems to me that xn, the solution of this difference equation, is some initial condition times r to the power n. Because if I start with x0, I get x1 from here. x0, I go to x1, and then to x2, etc. So this one I get. Oh, so now it's not anymore if r is positive or r is negative. This was the story here. Now, what is the crucial value of r? Okay, no. Okay, let's understand. Now, what will this xn go? That's my question to you. Think about it. If I ask you to tell me, what does xn do? You know you have this solution. Okay? And solution is this. What would you say now about xn? It's not exponential, like this, the linear. Here it is a little different. So, what does it depend on? If r is 1 is a little bit strange, r2, and 1 is at 1. If r is 2, what happens? You start here at x0, and the next x1 is where? At 2x0. Right? If this is 0 here, then you come here. Then you go where? 3x0. So you go away. Now 0 is again a fixed point. You go to 0, you stay at 0. No problem. But now the question is what happens to r. But now if r is greater than 1, we have instability. In other words, what happens? xn goes to infinity. Positive infinity. Let's suppose r is less than minus 1. Huh? Okay. So again we have instability. But how is the instability now? Well, first of all, you have something going to x0. Then you go to minus x0. Right? And then you go to x0 squared. Then you go to minus x0 squared. It depends if n is odd. If n is 3, r to the third is minus 1. 1, 1, minus 1. So if you are going to be greater than 1 in absolute value, so now we begin to understand r greater than 1 in absolute value, then we have instability. Either you go to infinity or to minus infinity, or you jump back and forth. So that's not a very good idea. We need an r that is smaller than 1. We have to stay there. And then you say, okay, but okay, let's think about it now, because what if here we have r times xn, but I'm going now to put also a term minus xn squared. This is a very famous equation. I write it this way. So it is like a population dynamics, because you see, this is the way animals live. They multiply, if r is greater than 1 especially, or they die. And so if r is less than 1, it's 0. Then you have minus xn squared. This is a death term, when these animals die. It's a minus. This is when they multiply. Usually for animals, r is 105. One animal has 5 children. And so then they start to die when they grow up. So this is a model of population dynamics, it's called. You'll find it in the books.
But on the left-hand side, do you have a derivative or xn plus 1?
Oh, you're right. I'm sorry. You're absolutely right. This is xn plus 1, yes. Thank you, Sergey. X of n plus 1. And here, I hope I didn't make no. This is all correct. Yeah, this is fine, what I was saying. The linear problems were here. Now we're doing discrete. So yes, you're right. Now we're doing discrete dynamics. You may think it's easier. Come on, no derivatives. Of course, on the computer you can do all you want, but do you understand the computer? It gives you an answer. Do you understand it? Do you believe it? So let's understand it mathematically. And the mathematical question I want to pose is, first of all, boundedness. I don't want the animals to die or to go to infinity, to multiply. It doesn't happen. What happens in nature? Animals grow in numbers, then they grow smaller in numbers in the winter. There is an oscillation in nature. So population dynamics means cycles. If I find cycles, I am doing something right, correct. If I don't find cycles, go to infinity, it's not a good model. So I want to understand the solutions of such a problem. And what kind of picture do I get from this? Oh, I will finish in a nice way. by generating the next time. Now, so what do? Let's plot this function now. This is f. This is a kind of dynamics. So if you think I want to plot this function, okay, let's move away from linear stuff now. We have a serious problem. It is this nonlinear discrete equation. So now, let's plot this function. And you see here, I have xn plus 1. And here I have xn. Correct? Now you see, this is population, so I don't want this to become greater than 1, it's negative. It doesn't make sense. I want to keep population x positive. So I want to stop here at 1. So 1, if you like, here, in a realistic model, this one could be 100 elephants can live in this region. Now we have 50, okay, xn is 50 elephants. 1 is the most you can have in this place. It's a nice model. Okay, so then what do I have to do? Well, x must always be chosen from 100 elephants to 0. So somewhere here. And the same happens for the next x. And this is xn, this is xn plus 1. And now look at the space.
Maybe it is better to write some constant instead of 1, because it's a bit unclear, I think, what you mean by 1.
No, it can be scaled out. Yes, no, you're right. Sergey, you can write Rxn and then minus another constant times xn, but you can scale things out.
Okay.
So this is problem is a one parameter problem. There is no need to introduce another parameter. Okay, so now we have a mathematical problem which is important, and let me show you exactly why R is all you need. You see, when, first of all, what happens when x is equal, then we have 1/2 here. And this problem has a symmetry about 1/2. Then it is very important to put the diagonal. Why? Because on the diagonal, if you are on the diagonal, it means you have a fixed point. Because if I am here, the diagonal is here, then I go to this point. Okay? So then I have to do, now let's think about a map. If you plot this map here, we're going to plot it for r less than 4, greater or equal to 0. So then you have this, this dynamics when what is so let's write xn plus 1 equals f of xn. Right? And that's equal to r equal to the time r times, f of xn comma r, I can write here, equal to r times xn, 1 minus xn. Okay. So now let me plot this function. Well, when r is less than 1, this function has this shape. First of all, you recognize these are parabolas, huh? X minus x squared, just a parabola. Okay, so we have a family of parabolas now, and there comes a point where is this true? We have another curve that passes by this point with 0 derivative, right here. And this happens, I think, when r is equal to 2, right? So when r is less than 1, oh no, when r is greater than 1. When r is less than 1, we are here. When r is greater than 1, we are here. And that will be, I think this is exactly r equal to 2, this curve right here. Let's remember that. Where is our function? Here it's xn, I say, equals 2xn, 1 minus xn, correct? So if you put here 1/2, right? You put here 1/2, you get 1/2, 1 minus a half, 1/2, times 2 is 1, so you are back at 1/2. So the maximum is here. That's again, this is xn plus 1, and if you put xn equals a half, you come back to a half. So here we are at this point, and now continue. because you can go up to r equal to 4. And there is another value r equal to 3 here. And there's the final one where you just touch the ceiling and come down. This is the most famous equation in discrete dynamics. If you know it, you understand chaos and many other things from this very simple equation. You see, you may say, why? Because nature doesn't need 1,000 dimensions. Nature, you can observe it with one equation, provided it's a good equation. It has deaths, it has multiplications, it has escape to infinity, it has many things. So your problem may be one-dimensional, but should be carefully studied, very rich. And these are the problems we are going to do together in this series. And I'll show you pictures of them some other time and many other things. But that's the way to begin dynamically, to study them. Is it clear? I only need a few more minutes, but everybody understands so far what is happening. Right, so that's the dynamics, what we want to do. And now, let me just finish this first part of the analysis by telling you, what did we say the most important thing about the dynamical system is? The first thing you study? How do we go? Fixed? Equilibrium, fixed points, equilibrium. So that is the first thing to study. Where am I sitting in equilibrium? And then you say, what if I do this? Are you going to fall down or are you going to go like this? Is it a stable equilibrium or not? So the first question is to study equilibrium points. What happened later? Remember, we studied periodic solutions. It was period omega and capital omega, they are rationally related. We get a periodic solution now. Aha! Can we find all this here? Yes. Can we find chaos, non-periodic solutions here? Yes. You will learn a lot of things, mathematics, from this system. Okay, so let me end today by simply studying the question of equilibrium. Now, let me erase it. Therefore, we erase everything, forget all of the stuff, and let's just study the equilibrium solution. I say, what do you think equilibrium means here? What does it mean to look for equilibrium position? What is the condition? For derivatives, remember, differential equation is that velocity is zero. Nothing is moving, dx dt is zero. Here it's not that. What is an equilibrium here? So let's start. The first point is equilibrium points. Okay. Later on, we will speak about periodic solutions, etc., etc. But let's start with this equilibrium point. What's an equilibrium point? Well, you see, that's why I drew this diagonal. Everybody draws this diagonal. If you look for this map, the logistic map, by the way, did I write it down? I think I did. It's called the logistic map for some reason. Logistic map. Otherwise people call it quadratic map because of this equation. What's the equation again? Here it is. Well, not here, not exactly. I forgot to write down the parameter x times xn, 1 minus xn. Okay, what do you think is an equilibrium point here? For a map like this, there's no derivative. So equilibrium points must satisfy. If I am at an equilibrium point, I stay there. Right? So, equilibrium point means x bar equals f of x. Bar, yes, just, or x, I can call it x. Right. So it means you give me x, I give you back x. F of x is x. That's equilibrium. Where are the equilibrium points? At the intersection of the curve with the diagonal. What's happening here? You give me this point, I give you back the same point because I'm on the diagonal. So don't forget to keep in your mind, this is a very important player in this game. The diagonal. We always write the diagonal because it gives you here. What happens here? Well, let's see. Is it right? Let's go to this equation. When r is equal to 2, I said that. So we have the equation xn plus 1 equals 2xn 1 minus xn. I claim, but we just did this. If I put 1/2 here, I get back 1/2 because I'm here on the intersection. Now, what happens if you put r equal to 3? So let's put r equal to 3. xn plus 1 equal to 3 xn 1 minus xn. Okay, so what is equilibrium? Means x equals to 3x times 1 minus x. Correct. All the solutions are here. But where are these equilibria? Then for this curve. Which is the curve I'm talking about? I've painted red. I'm talking about now this curve. R equal to 3. Observe that this curve crosses the diagonal at 2 points. This is the trivial point. So when x is 0, of course, we know it's 0. What is the non-trivial point? The non-trivial point is 1 minus x. Meaning that this is, one minus x. What does this difficult equation gives me? 1 equal to 3 minus 3x, right? So this gives me x equals to I found it. I just found it. This point here is located at 2/3. And there is the fixed point. So now geometry and algebra are together. We can use algebra to find the fixed points, but also geometry will be very useful to us. And now, just finishing the topic is, what is the next question we ask? Remember, I spoke about equilibrium points. What property did I want to study? Give it this?
Стабильность. Ну да, когда типа к стабильности.
Right.
К чему стремятся?
Stability. If you're here to the fixed point, are you going to go to that fixed point? Okay? So if this fixed point here means that so much population of elephants will live there, stable, for a long some time, if it is stable, then even if you have, instead of 350 elephants, they will die back to 300. When one season you have 250 elephants, they go back up to 300, because the point is stable. So what should solutions do here? Go approaching the fixed point. So stability is a geometric property. I now follow the geometry and I tell you what will happen. So let's see what happens if r is equal to 2. So what is r? R is the rate at which the elephants are born. They are born with the rate r. But they also die because there is an xn square. So that subtracts elephants. But they grow like any other animal. They grow exponentially if you are alone by r. So let's see how do we follow this dynamics geometrically. I take how many elephants you want? Very few. You see, if I have too many elephants, near the idea of 500 or something, the most elephants I can have, then look, after 500 or 400 animals, let's say, I go to the point, and then to find the next point, I must go to the diagonal. Diagonal. Even the diagonal, I have the next point. So then, I make this point here my next point. So this was x0, and this now is x1. And you see, they died because there were too many. They couldn't live so much. So they fall down. That's why this is called, in biology, a curve of competition of the species who die and live and die and evolve in nature. So what happens is here. So then, what is the next? Well, the next, after I'm here, I must go back up to the function and go here, to the diagonal, then here, then here, then here, then here, and then I find out that all my elephants will die. In other words, unfortunately, this value of r, which is r equal to 1, is exactly tangent here, or below 1, r below 1, it does not allow for the animals. It's not big enough for the animals to grow to a big number and stabilize there. Yeah, because if r is equal to 1, say one animal gives birth to one pair to only one child. So the other two only one child. It's not good enough. You must produce more children so the population will be more stable. Okay? So you say, suppose 2 children came out of the family. Then we go to r equal to 2. R equal to 2. So let me start here with x0. Now I go to r equal to 2, I'm here. Okay, which is here. But now, forget what is here. We follow a path. Diagonal function. Diagonal function. That's why go out there. We know the sequence is x0, this is x1, then we go to find x2, then x3. The equilibrium is stable. Then elephants will learn to live at 1/2 of 500 and will be 250 very happy there by this. Is it true if we make R too big, we have too many children, and that there is not enough food for all of them? So for some point on, some of the animals must start to die. Let's take, for example, this was R exactly equal to 3, right? What do you think will happen at R equal to 3? Well, let's see. What happens at R equal to 3? We can play the game completely geometrically. Start with the same x0, let's say here I start with x0, I reach the red function. Now I go to the diagonal. Now go to the function. Now go to the diagonal. Now go to the function. Oh! If I fall below the right level, then my next point will be on the diagonal here. And then if I go to the next point, I'm here and here and here. Oh my God, unstable. This will be unstable. I'm going away from the fixed point. But if this point was here, let's say, very safe, we saw it. But if not, I told you this r equal to 3 is true. It's just exactly on the point of changing. But suppose I told you this was r equals to 0.8, a little below r equal to 3. What's the other situation? I'm here, here, but now I fall somewhere inside and inside, and the spiral is moving in. That would be stable. So what is the condition of stability at that point? What is the condition of stability? The condition of stability, my friends, is simply that. When you start with some function, fx of n, it should be very easy to understand. We put xn equal to x bar plus, what does this remind you, the beginning of the lecture? I made a little perturbation, right, but now this is xn. So let's put it here. What do we find? Xn plus 1 equal to what? The value of f prime at xn, at equilibrium, times, here is the Taylor series. So we are not going to worry very much about higher orders, but there is the linear equation of stability now. So all we have to do is look at the derivative of the function. And if the derivative is bigger in absolute value, bigger than 1, then you see if the derivative is bigger than 1, just think about it yourself. You have a function here like this, and you make a derivative a little big here, bigger than 1. So there is now the diagonal right here. So I'm coming here, and what's happening? I'm here nearby, I go here, then I fall down here, then I go back to the diagonal, but now I'm falling because the slope is big, it's bigger than 1. So what happens here? This is the criterion of stability. What is then stability is if the function has a derivative smaller than 1 in absolute value, could be minus, negative, that's okay. It's negative. So what happens here? There is your diagonal passing by this point. Okay, now you start. You come here. Now then you go to the diagonal. Now back to your function here. But now you're inside. diagonal, function, function, diagonal, function, diagonal, function, diagonal, you're now going in. The slope is the deciding factor. Stuff. Okay, this is the beginning of the story. And I think you will enjoy it later on also. If you like, we can next week also, we can continue. And pretty soon we can see some things very, very colorful about nature, about life, about lots of interesting problems of chaos. Yeah. Okay? I think
Thank you very much.
it's a good beginning.
Это в теории цепных дробей получается? Да?
If you have...
Это цепные дроби получается, судя по тому, что они выходят?
Ah,
Нет. Нет? Понятно.
you're saying if this is periodic.
Да, this periodic.
Yes. How it's called? Continual fractions.
Yeah.
Continual fractions. Yeah.
No, I do not see.
So,
Ну ладно.
not, yeah, you mean what will happen here? There is, that's what we will do next time. There may be a point, there will be a point here, let's say, at this level, here.
But maybe you could separately magnify this this box right there separately, because that's his question. What?
Yeah, yes. Yeah. Okay, so let me simply redo this a little bigger here.
Well, not necessarily the whole figure, but the.
Yeah, but that's what no. I need to have also this big. Here. Okay. So now let's say the diagonal is here. Wherever the diagonal. This is the fixed point, right? Now here is a question. It looks like -1, very close to 1. But if it was more level or less level, it could be stable. Could be stable. Could be unstable. Of course, if I draw it lower, the mountain here, well then you know, here the slope is very low. If I drew the mountain higher, here, you'd say, oh, but here the slope is bigger than 1. So, in between is this case of just stability, f equal to 1, just the case where you have to decide between the two. The thing is that, what about a periodic solution? Something that begins from here, gives you a point here, and then comes back here. That's what I want to discuss for you next time, of course. But anyway, suppose I'm here, I go to the function, I go to the diagonal, then to the function, I go here. Now, if I'm too far, see where is my first point? I could come down now to a point here, let's say, and then go here, and start the same process again. That's a periodic orbit. Now, we have to look at them a little more carefully. It doesn't look nice very much like this. But you can, I'm telling you what is a periodic solution like. There is your middle line, at the middle, the symmetry. And I tell you, the independent of stability. Now I go away from a fixed point. Now fixed points we understood. If the fixed point is stable, you know you're here. The slope is less than 1. So the question, stability condition of a fixed point, stability, you can write this down. Stability of the fixed point, x hat, let's call it, is this. The absolute value of the derivative of f at x hat must be less than or equal to 1. Equal is a very special case where you keep turning, you don't even go away, you don't even go closer. It's in between. So the condition is this. So if you don't like the equal sign, then definitely less you will go to the fixed point. So if absolute value of f prime at x hat, so here we have stability. What is the instability? This is bigger than 1. The slope, if the slope here is bigger than, like here, the slope is bigger than 1, no way, there is a fixed point here. Of course there is. But no way it's going to be stable. You go to this one, boom, you go away. Okay? So this is the question of instability. Right? But even if we understand fixed points, we don't know anything about the problem because it has infinitely many periodic coordinates. Now, imagine like this one, what I was doing here, for instance. You have a map like this, and you have this is a diagonal, all the way through the diagonal, and any map like this. What do you think is a fixed periodic orbit? To get a periodic orbit, you must go, we go to a point here, to the diagonal, and then somewhere else. And if it's a fixed point, you start from here, you stay here, because you're on the diagonal. That's the fixed point. What about period 2? Period 2 must be starting from here. Yeah, let me see. Okay, let's see. Let's suppose I start from a point just below the middle point. I come here, I look for the diagonal, I come here. Now, I go down to the function, and I happen to fall at this point again. Then I am creating a rectangle on the picture, where from this point I touch the diagonal. I go all the way up here, then I go to the diagonal, then back to the function, then back to the diagonal, and I am finding myself at the same point. So there is a x1 hat periodic orbit, and there is x2 hat other point. F of x1 hat will give you x2 hat, and f of x2 hat will return you back to f of x1 hat. And that's a period 2. Orbit of period 2. Imagine the whole world is opening now. Periodic orbits, stability, and all that. You may say, oh, who cares about discrete dynamics? Xn goes to xn plus 1. But in the first part of the lecture, I explained to you. All you need to do with harmonic oscillator, just give him a push by a sine omega t, and you have to do discrete dynamics. You have to look at the intersections. You take a plane, and you look at the intersections of the orbit. When is it coming back to this plane? If it comes back to this plane, what do I care if it travels around the universe? I want to stay here. And then I see, comes here, 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 the Earth is here, and the Moon, and the Earth and the Moon is here, here, here. So it's stable. So the Earth and the Moon are always around here. After they go around the Sun, they come back. So discrete dynamics is very important to understand. Okay, I think I kept you a long time, but I hope. What was your first name again?
Dennis.
Huh? Dennis. You said it with a D. Yes, but Dennis, you must agree that now we are above high school, right? We didn't. You didn't hear this in high school.
I didn't.
No. Okay.
Yeah.
So that's why you're in university now. But you were right that everything about the harmonic motion and the things we learn in high school are very nice. We learn about derivatives. Everything's continuous and beautiful. And here you see, it's not differentiable. Now it's discrete. And it's very, very important to understand. So, okay, I think you will learn a lot next time also. Okay, guys. Спасибо большое.
Thank you.
До свидания.